Okay, so we're going to jump back and do lesson 28, which I forgot to do in class from last week's notes. So make sure you have last week's notes and fill them in. So we're going to talk about factorial notation in certain realms of mathematical study, including probability, statistics, counting theory, game theory, a lot of different kinds of math. It's necessary to count combinations and permutations of things. So like in probability and statistics, in order to figure out how likely something is to happen, you have to know how to count the number of ways it could possibly happen. And to do that, you have to, and it ends up that what you have to do is you have to multiply a lot of strings of consecutive factors together. Just like this situation here, if you were going to pull a 13 card hand out of a 52 card deck, the number of possible hands you could get would be this big giant fraction here. 52 times 51 times 50 times 49 times 48, 47, 46, and so on, all the way down to 40, divided by 13 times 12 times 11, and so on down to 1. So because we want to be able to use computers and calculators and things like that to calculate these humongous things that we sometimes deal with, we want to have a notation that a computer can understand, or a way to write this kind of expression more succinctly without having to write all those numbers out. And so that is where factorial comes from. Factorial is this little exclamation point, and when you put it after a number, it just means to multiply that number by all the counting numbers beneath it. So here's the example, a very simple example. 5 factorial is equal to 5 times 4 times 3 times 2 times 1, which equals 120. So that's what that little exclamation point means. If you see it after a number, it just means multiply that number by all the counting numbers below it. All right, so these two examples right here we're going to do, they are just going to kind of give us an idea of how factorials act, how we can simplify fractions involving factorials, and how we can write fractions to simplify a big factorial expression. All right, so these two examples are just to get an idea of what's happening here. All right, so we've got 9 factorial over 3 factorial times 5 factorial. And you could just punch this into your calculator, but that's not the point of this problem. The point of this problem is to help you understand how factorials act so that you can then use factorial notation to write a very complicated expression in a more simple way. And if you do this on your calculator, you're not going to learn how to do that. All right, so this is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 5 times 4 times 3 times 2 times 1. That's what that equals. All right, you can see here that I've got a 5, 4, 3, 2, 1. I can cancel all those factors because they're all the same. And then I've got 3 times 2, which is 6, so I can cancel that. And I'm just left with 9 times 8 times 7. And I could punch that into my calculator, and I would get 504. Okay, so you see how that canceling worked there. Here's another example where we've got 14 factorial over 6 factorial times 11 factorial. I could sit here and write 14 times 13 times 12 times 11 times 10 times 9 and so on, but I'm actually just going to stop at 11 and put a factorial right there, because that means the same thing as 14 factorial. 14 times 13 times 12 times 11 factorial, which is 11 times 10 times 9 times 8 and so on down to 1. So I'm going to write the numerator that way, because that way I can cancel the 11 factorial that's in the denominator. And then I still have the 6 factorial down there, which is 6 times 5 times 4 times 3 times 2 times 1. So you can see that if you just want part of a factorial, you can divide by the lower part of it, and get rid of the numbers you don't want. And that'll make more sense in just a second. So now we want to cancel whatever we can here. We've got a 12 on top. There's a 12 on the bottom. We can cancel that. We've got a 2 with a 14. That leaves 7. And that's about all you can do. So that is going to be 91 over 30. Okay, so this is a very simple example to show how you would write a complicated expression more simply using factorials and using what we just learned about canceling in fractions. So you got 11 times 10 times 9 times 8. And the question is, how would you use the factorial key on your calculator to evaluate that? Well, it doesn't have a factorial in it. And it's not 11 factorial because it's missing a bunch of the numbers. So if you wanted to use your factorial key to work with this, you would have to rewrite it as on top. You could call it 11 factorial, but the thing is you don't want the 7 times 6 times 5 times 4 times 3 times 2. You just want these numbers. And so if you divide by 7 times 6 times 5 times 4 times 3 times 2 times 1, you will have 11 times 10 times 9 times 8. This equals 11 times 10 times 9 times 8. Because even though this 11 factorial on top has all the numbers down to 1, if you divide by 7 factorial, they will cancel with the 7, 6, 5, 4, 3, 2, 1, and you'll just be left with that. So that way, now you can plug this into your calculator very simply by hitting 11 factorial divided by 7 factorial. Now, this wasn't a very complicated expression to begin with. It doesn't seem like such a great benefit to be able to use the factorial symbols. But if we went back to that problem where we had, wait a minute, where did it go? This, and you see that you can take this big, ugly expression and write it like this and punch it into a calculator quickly. That's a big difference. So that is what factorial notation is for, is to be able to take expressions like these and write them in a more simple way that can be quickly punched into a computer or calculator. All right, abstract rate problems. These are just like any other uniform motion problem, except now we are dealing with only letters. And in the problem, they will give you some letters that for different aspects of the problem. And those are the only letters that can appear in your answer. So that's the kind of the tricky part about it. So always stick with the fact that rate times time equals distance. This is what we know. And this is what we're going to use to do these problems every single time. But we're not going to use R, we're not going to use T, we're not going to use D because the problem will give us different letters. And so we want to use those letters and make sure our answer only involves those letters. Okay, so this says that the train traveled m miles at p miles per hour and still arrived 1 hour late. How fast should the train have been traveling to arrive on time? So first of all, they tell us that the train traveled m miles. That's the distance, m. It went at p miles per hour. That's the rate. They don't give us the time. They tell us that the train arrived an hour late, but they don't tell us how long it took the train. They don't tell us anything about how long it took. It just says it's an hour late. So instead of trying to deal with that right now, we're just going to write the time as a function of the distance and the rate. So time is equal to distance divided by rate, since rate times time equals distance. So I will write the time as distance, m, divided by p, the rate. So now I have the rate, I have the time, and I have the distance. That's the original situation. That's what happened with this train. It went this rate at this distance, and it went this amount of time, m over p, and that was an hour late. You want to see, well, how could it have arrived on time? So the thing you want to change here, you don't want to change the distance. The distance is not going to change. You want to change the rate, but you don't know how much to change it. It doesn't tell you. So the only thing it actually tells you about is the time. It tells you that this time here that was taken in the original situation is an hour too much. It's too late. It's too much time. So in your new situation, you want your time to be m over p minus 1. You don't want it to be m over p. That was too much. Subtract 1 from it. That's the time you want. You still want the distance to be m. And the question is, what rate would you need to make that happen? And so now you can figure out the rate because you've got the distance and you have the time. rate is equal to distance divided by time, since rate times time equals distance. So the rate would be distance, m, over the time, m over p minus 1. And this is the answer, but you wouldn't leave your answer as a complex fraction. And that's why partly you've been looking at simplifying complex fractions up until now. So you have this fraction m over p minus 1, and you don't want that to be complex, so you want to get rid of all the little denominators. And to do that, you just need to multiply the numerator by p and the denominator by p, but sometimes it helps people if I write p over 1 and p over 1. So we're going to multiply this numerator and denominator by p over 1. If I multiply the numerator by p over 1, I just get mp over 1, which is just mp. The denominator, I'll need to use the distributive property. So p over 1 times m over p, the p's cancel and I end up with m, minus, now I'm going to do p over 1 times 1, and that is just p. So p. So this is the new rate. This is the rate you want in order to get there on time. So mp over m minus p miles per hour. That would be the answer. Okay, here's another situation. The ship traveled k miles in t hours and was 40 miles short of the goal. All right, so I'm just going to draw a picture here just to make sure. Oh gosh, that's not a ship. So a ship, we'll say, look, this kind of looks like a cruise ship, so it's not really the kind of ship we're talking about. But anyway, so it goes, it's 40 miles short of where it's supposed to get. All right, so again, rate times time equals distance. So let's see what information they gave us. They said that it traveled k miles, that's the distance, in t hours, that's the time, and it was 40 miles short of the goal. So the k here is this distance, how far it went this first time. And the rate, they don't tell us what the rate is, so we can write the rate as distance divided by time. So k over t was that rate. Now, what do we want to do? If the captain could try again, how long would it take to reach the goal? So now we're talking about reaching the goal, which is right here. He didn't reach the goal that time, it was k. He only went that amount of distance. We want him to reach the goal, and we want to raise his rate by 10 miles per hour. So the question is not, how can he reach the goal? But the question is, if we raise his rate by 10 miles per hour, how long is it going to take him to get to the goal? All right. So again, rate times time equals distance. The rate now, we're changing it to k over t plus 10. We're increasing the rate by 10. The time is the question. We don't know. The distance now is not going to be k because he's going to actually get there. So it's going to be k plus 40. All right. The time is what we're looking for. And now that we have the distance and the rate, we can just write the time as a function of those two things, distance over rate. So k plus 40 over k over t plus 10. And that again is a complex fraction. So you've got k plus 40 divided by k over t plus 10. And you will have to multiply that fraction by t over t. All right, so numerator, going to do the distributive property. K times t is kt plus 40 times t is 40t. And then in the denominator, when you multiply t times k over t, the t is going to cancel and you just end up with k. And then you've got a plus sign. And then when you multiply t times 10, you're going to get 10t. So that would be the new time. That would be how long it would take, and that is hours. So the key important thing about these kinds of problems is that you don't want to have any other letters in your answer besides the ones that are given to you in the problem.